Good morning. My name's Nick, and firstly, apologies, I'm doing this via a video. There's a storm here, and really annoyingly, my flight's got delayed by a day. So fingers crossed, whilst you're listening to this, I'm on my way over the Atlantic, and I'll be around for the rest of the event from the second day onwards, from the Tuesday onwards. So please do grab me, and it'd be great to chat about some of this when I arrive. Now, I'm at EPCC, which is at the University of Edinburgh, and we are the UK Centre for Supercomputing. So we've got some very big machines, but we're also interested in new potential technologies that will be on our machines in the future. And really, that is my interest here. So as well as hosting a testbed in Edinburgh, I also chair the HPC SIG, and I've been working with a testbed in Edinburgh for about two and a half years now. So it gives me a reasonable view of sort of where we've been, where we are, and maybe some views on where we should think about going. But obviously, it's great to get feedback from the community on these things. Now, I appreciate I'm going to teach some of you to suck eggs here, but it's worth just making sure we're all on the same page. High performance computing is traditionally very large supercomputers housed in dedicated facilities, such as up here on the top right. This is one of our machines. This is the UK National Supercomputer, and it's built out of commodity parts. So CPUs from AMD or from Intel, GPUs from Nvidia or AMD, but there's lots and lots and lots of them. And in addition to that, high performance networking, high performance file systems. Now, the machine itself is clever enough, and for instance, this is the insides of a Cray, but also what's very, very impressive is all the infrastructure around that. So for instance, on the bottom right, this is in our facility, and this is all the power that brings the machines to life. And we have something like 40 megawatts to site in Edinburgh. So there's a lot of power that we have for these machines, and they need it. And these cost a lot of money. We're talking about hundreds of millions of dollars. And in the HPC community, there's been a recent push towards exascale, and that's the ability to compute with a billion floating point operations per second. We're just about there. Thereabouts. There's a couple of machines in the world that can do this now, but we are very much moving further and further into this era. We're just at the start of that era, and we will see more and more machines coming online that can do this. And traditionally, HPC is associated with scientific computing workloads. And it's not an exaggeration to say that every recent scientific discovery has, to some extent, involved simulation, numerical simulation. I've got some examples here. For instance, computational fluid dynamics for a jet engine. This is a project we do in Edinburgh looking at simulation of a jet engine with Rolls-Royce. Down here, this is turbulence from wind turbines, so to be able to design more effective wind turbines. And then here in the middle, this is modelling the Earth's geomagnetic field, which changes continually, but is very important for a variety of situations and use cases. But surprisingly enough, the scientific computing community is very, very conservative. Around 65% of codes, there or thereabouts, running on our supercomputers are written in Fortran. And, a lot of these are pretty old codes, have been around in some guise for 20 or 30 years. Now, typically these machines are driven by the command line with batch submission. So you prepare a job submission script, submit it to the queue, and the results are made available via the file system. And you do this via a login node, and there's a module environment which manages compilers and different libraries. So yes, the rest of the community is moving to the cloud and embracing things like containerization. Traditional HPC and scientific computing is moving slowly, and that's a nice way of putting it. Still very, very stuck in the traditional ways and moving away from them can be quite a challenge for a lot of users. And almost exclusively using MPI and OpenMP for parallelization, and then some technology on the GPU like OpenMP, OpenACC, or something specific to the vendor. And I mentioned GPUs because this has been quite an impact for the community. There's been an obvious requirement to move to this technology, and over the past 10 years or so, a phenomenal investment in the codes to move them onto these accelerators. And it's a game we've needed to play in order to move towards this exascale I mentioned before. Because machines like Frontier at the top right there, well, they are very, very heavily GPU oriented. And as I say, this has been a huge amount of effort from the community, but it's far from perfect. There's pragma approaches which are general across different devices, OpenMP, OpenACC. These are generally quite well supported, but the performance is nowhere near as good often as going with vendor-specific solutions. So CUDA for Nvidia and ROCm for AMD. But the problem there is you've then not got the portability across the GPUs. You're then stuck in this specific ecosystem. So yes, there's a lot of work going on, but there's still quite a few challenges to solve there, and maybe some issues that we're creating for ourselves in the future. But GPUs have been a disruptor, and there's some important lessons we can learn here. It's really interesting, I think, that Nvidia invested very heavily in the software ecosystem. So yes, CUDA, but also a lot of work on optimizing libraries and key applications. And so in HPC, most often when you talk to people about Nvidia versus AMD GPUs, they don't often talk about the hardware. Instead, they're talking about the software ecosystem. And that's really the emphasis that they put on that. And I'll talk about this later in the context of RISC-V. I think this is an important lesson for us to observe and bear in mind. And also, we are increasingly seeing increased emphasis on energy efficiency and sustainability, technology sovereignty, and the line blurring between AI and traditional HPC, traditional scientific compute. Now, I'll mention this a bit later on in the talk, but activities such as the European Processor Initiative, this is hitting some of these points, certainly around the technology sovereignty. And again, maybe these areas are where RISC-V can really have an impact and have an influence. Because, it's not enough for RISC-V just to be as good as what we've currently got. And the reason for that is supercomputer center operators really don't like RISC. And it's fair enough. They're spending many millions on a new HPC machine. I'm completely stealing the phrasing here, but in HPC, nobody got fired for buying x86 CPU with NVIDIA GPU. So new technologies really is a challenging proposition, and how we phrase these and sell them to the HPC community is very, very important. So I think in this RISC-V community, what we need to focus on is what problems can be solved with RISC-V that can't be done today with existing solutions. Because realistically, if you can already run it effectively on an existing GPU, well, do so, because there's been lots of investment on them already. Why RISC-V for HPC? What are the new things that this can deliver and add? And maybe one of these things is the integration of the CPU and accelerators, for instance, with a common ISA across them. We're seeing work such as work from Barcelona Supercomputing Center on some really exciting things that are combining these together, and there's other things out there as well that will then view these accelerators as vector units, very wide vector units, driving them from the CPU. And, I'll talk about some of these general things again a bit later on. Now, in HPC for thinking about moving to RISC-V, there are a couple of HPC-focused RISC-V testbeds out there. The first of these, down at the bottom right, is Monte Cimone. I hope I'm pronouncing that right. It was developed by E4 Computer Engineering in Italy and then deployed in Barcelona Supercomputing Centre. And that used some of the original Hi-5 boards. In EPCC in Edinburgh, we've also got a RISC-V testbed, and we have a mix of technologies on that. Now, I'm going to use the testbed up in Edinburgh really as a bit of an example, just because I know it best. And I think it's quite interesting to look back, because when we initially set this up in 2022, really things were rather different, because hardware availability then was a big challenge. And I'm not talking about hardware availability for high performance computing with RISC-V. I'm talking about just general, give me a RISC-V physical thing I can run on. So we absolutely had to rely on single board computers, designed more for embedded workloads typically, and often these were sourced from China. We then brought them in and hooked them up. So a long way away from high performance computing in terms of the performance, but still, getting the technologies, the libraries, the compilers on there, letting people kick the tires, actually running with their codes on this technology, even if they're not going to get the performance that they'd expect on something more traditional. Now, at the top left image up here, you might see the Hi-5 board up at the top, and that's really interesting in itself. But equally, again, a few years old, and the performance quite considerably less than what we'd expect in x86 or ARM, for instance, for high performance computing. Now, when we started doing this, deceptively simple initial steps, I think, is a good way of summarizing our initial experience. Because when you look at a diagram like this on the right, it actually looks pretty impressive. There's a lot of technologies, libraries, compilers, other things, applications, for instance, that have been built for RISC-V, and I can put the Linux distribution on, and I can just install it and go for it. And that's great, but when you start moving away from the standard assumption, this is then when things start to become more challenging. And the reason for this is we bought all these boards and we wanted to expose them just like any other HPC machine. We wanted it to be boringly familiar to the users. These are the compute nodes. We've got a login node managed via a batch queue system called Slurm, and they just submit their jobs, they run, and the shelled file system then has the results. And whilst actually all these individual bits and pieces have been ported over to RISC-V, which is great, where we started to have challenges was things like on the boards that we bought. Well, it was non-trivial to recompile the kernel and also have a new bootloader, which was required for the new kernel. And that required a lot of work, not least because all the instructions were in Chinese. And I was very lucky. One of the people working for me was from China, so he understood all of that. But still, a lot more difficult than we'd originally anticipated, because it was a bit like going down a rabbit hole. And, again, this is just the maturity side of things. And the simple fact that these things were not designed with HPC in mind for this. And of course, a lot of these have been built and optimized at this point for standard ISA without aspects such as vectorization. So again, wanting to go that extra step, which is very important in HPC, well, now we're non-standard and we do it ourselves, and it makes things more complicated. I think it's fair to say that things changed for us quite substantially towards the end of last year. And that's when the SG2042 was released. You've probably heard of it, I'm sure you have. It's commodity available, 64-core CPU, and it comes in a couple of form factors, if you like. The most common one is the Milk 5 Pioneer workstation, sold by Softco, and you can buy that and they'll ship it to you. As I say, it's for general purpose availability, and I think very reasonably priced. But there's also other people building solutions around these technologies. For instance, E4 Computer Engineering developing solutions around the CPU, just like they had previously from Montage only around the Hi5 technology. And I know E4 are around at the summit, and I'm sure they'd be happy to discuss that side with you. But we focused on the Pioneer workstation just because that was available at the time. And the first thing we did is we said, okay, what we'll do is we'll take some of these other boards we've got in our test bed, and we're just going to compare core for core. So a core of the SG2042, called the C920, against a core in each of these other technologies. And the reason we're doing it core for core is because obviously they've all got different numbers of cores. So it wouldn't be meaningful at that stage to do full processor runs, because of course 64 cores in the 2042 would be very different to 1 or 2 cores in some of these other technologies. Now, what we did here is we ran NASA's MPB parallel benchmark suite, and these represent the key kernels in computational fluid dynamics workloads. And higher is better. Now, in red, for these other technologies, this is the percentage performance of the SG2042, a core in the SG2042, that it's achieving. And you can see here, for instance, in the Vision 5 V2, it's achieving between about 21% and 38% the performance of a core in the SG2042. And by comparison, that tends to be the best. And the others are worse. So here, for instance, the V1, well, that's quite a lot lower, from 6% to 24%, and similarly here. But really the point I'm saying is the SG2042, a single core, is a very significant step up in terms of performance than what we had until that point, commodity available in RISC-V. So, a much more serious proposition potentially. But really, to answer that question, what we had to do was benchmark this against other architectures that are more commonplace in HPC. So we compared this against AMD part, that's in Archer 2, the UK national supercomputer, an Intel Skylake, that again we have in a machine in Edinburgh, and ARM Thunder X2, which is a couple of years old now, a few years old, but again, interesting just to compare what they're like on that. And so we ran all of the suites, but just for the purpose of time, I'm just going to compare 2 benchmarks. The first is embarrassingly parallel, which is compute bound, and the other is integer sort, which is memory bound. Now, the black line is the SG2042, and we're scaling the number of threads here with 1 thread per core. So that's why, for instance, here the Skylake stops at 26, it's only got 26 cores. And what's really fascinating, I think, here is the Marvell Thunder X2 and the SG2042 are pretty identical. They map pretty identically, but then the greater numbers of cores makes a difference. And yes, the Intel part and the AMD part here for the EP benchmark, there is a performance improvement, but it's not that big. The fact that we've got 32 and then 64 cores on the SG2042, well, actually that's very important compared with the Intel part, which only has 26 cores. But this is completely different for memory-bound codes, and we see this time and time again. It isn't just this one benchmark, where the SG2042 is really starting to struggle here, is really lagging. And so clearly that is the bottleneck on the technology. It's really great on that compute side of things, but when we're looking at the memory side, well, that's where ideally, hopefully, the next generation will be scaled up. Now, this is a very quick overview, a lot more detail at that paper there, and you can also, as I say, grab me the rest of the event, and I'd love to talk about this in more detail. Now, that's a very important step for RISC-V, but I think arguably where we're going to see RISC-V gain inroads, certainly initially, is more on the accelerator card space. And that's because it's actually much lower risk. You can buy one of these, slot it into an existing system, and you're good to go. And there's also already several accelerators out there, one from Esperanto, one from TensTorrent, Inspire Semiconductor have announced theirs, which will be available later in the year or early next year. So I think this is something really important for us to be aware of and keep track of. And in our testbed in Edinburgh, we've got a number of TENS torrent, PCI Express accelerators. So we've been experimenting with these. And they're available, you can buy them today, and I think really very reasonably priced as well. Designed around this idea of this 10-6 core, where each of these cores, these 10-6 cores, has 5 RISC-V cores, 3 that drive an FPU, quite a wide FPU, and 2 data movement cores. And this really goes back to my point before around what's the value add of RISC-V for HPC. Well, potentially the answer to that is using a technology like this, I can have a bespoke data movement and compute. So I can really drive that differently for my application if my application, for instance, is latency bound. And I can have these different components running concurrently in a pipeline just for different bits of input. So maybe this can help get rid of some of the memory bound aspects of our codes. So we experimented with a TENS torrent grayscale, for instance, for a stencil-bound code. Stencils are ubiquitous in scientific computing. So this was a very simple Jacobi solver, but crucially it enabled us to explore some of these algorithmic properties in more detail. Now, and it's sort of to be expected, our initial version, without any experimentation or porting, was much, much, much slower than a single core of a Xeon Platinum Cascade Lake. But then what we did is lots and lots of work on the technology itself, and eventually we managed to get a very significant performance improvement. In blue is one 10-6 core, and what we ended up with was about 160 times what we'd had initially. But then over all 108 worker 10-6 cores on the Grayskull, we were actually able to slightly outperform the Cascade Lake, the 24-core Cascade Lake. But crucially, at 5 times less energy. So again, it goes back to my point of, these are really nice sort of case studies. It's quite early on, but this is the value add. We can potentially deliver this increased energy efficiency through specialization. And once we've understood exactly how to structure the codes for the technology, actually the performance is pretty impressive. There's a lot more detail about what we've done here and all the different steps on this link. And again, as I said before, please just grab me the rest of the summit. I'd love to talk about it in more detail as well. So what we've also done is a whole load of interest from the HPC community. We've organised a whole load of workshops at key HPC events. This is Mark Himmelstein, the previous CTO, giving the keynote at the Supercomputing workshop last year. What was really nice is HPC Wire, the main HPC community publication, then wrote an article about all of this. And the reason for me telling you this is there was a lot of interest here in the HPC community around RISC-V. What is it? Why is it interesting? As I say, we've had 4 workshops so far. We've got another next month at Supercomputing. Be great to see you there. And we've had another accepted for HPC Asia early next year. And again, please do consider submitting something to that. The call for papers will be out very soon on that. So some reflections to finish off with. Where do we need to go? There's a common view that HPC and scientific computing are the same thing. And I don't think we should stick with this in RISC-V. I actually see high-performance computing as the layer underneath AI, machine learning, and scientific computing. It really is what enables these things built on top of that. And that's really, really important because we're seeing a lot of vendors coming out now with accelerators and technologies targeted at AI and machine learning, but actually a lot of what they're doing can also work very well for scientific computing. So, actually, let's also gain benefit in that community with what's happening over there. And it's also very important, I think, with things like the matrix extension work that's going on, let's not just have that utterly focused at AI and machine learning, because these matrices processing these is very important also for scientific computing. So again, this powerhouse that enables us to do these things built upon that. Software ecosystem is very, very important, crucial. And if we subscribe to the view that accelerators are likely to be the first thing that are going to be adopted by HPC, that is RISC-V, we need to address programmability. Now, currently, each accelerator vendor has their own toolchain, an API. Yes, it's great that they're being able to build upon some of the common RISC-V ecosystem, but you've still got to learn their framework. You've still got to program using their technology. And I think we've got an opportunity to unify these across the vendors. It goes back to this point that Nvidia have invested very, very heavily in the software ecosystem for their accelerators. But we, as the RISC-V community, don't have those same resources. So we need to pool all the different resources, I think, for the vendors to be able to say, look, let's have this common layer. Maybe it's a standard set of libraries. Maybe it's standard program models like OpenMP that we support across all of these that then helps pool the effort. And it means we're not reinventing the wheel, and we can go from one accelerator to the other. And we've got this rich ecosystem. Also, on all the libraries, as I talked about before, it's a lot more nuanced than just an image and what's out there and you can download. A lot of these are not optimized for vectorization. I think there's actually a lot of low-hanging fruit and really quite a few things that we can do to a handful of libraries that will make a big difference to the HPC community. And we're currently in the SIG looking through each of these and really understanding where the gaps are, and it'd be great to have people's involvement in that. Profiling and higher level lessons learnt as well. So firstly on the profiling, utterly critical in HPC to understand where our bottlenecks lie in a code. There's been some work here from Barcelona, but we need a lot more. We need a lot more for support for tooling, common tooling here, and also vendors to make a richer set of hardware counters available. And then the RISE guys at the bottom, this is excellent, but it's lower level than what HPC developers would want to engage at. So I think there's a lot of opportunity for to think about best practice at the higher level. So thinking about software development for RISC-V and HPC and what we can do here. And lastly, mature support for fast networking. This is crucial. InfiniBand is really important, and there's been work done by tactical computing, but there's other HPC communication technologies too. We really need these to be matured as a priority so we can build scalable solutions out of these different RISC-V technologies as they come about. So thank you very much for listening. Things are progressing quickly, very, very exciting, but there's still a lot of work to do. There's the why. What's the value add? Why would you adopt RISC-V for HPC? Really a call to action. Please join the SIG, get involved. As I say, we're doing a gap analysis to understand where we need to apply different bits of effort going forwards. We're doing some marketing activity. So if you're in that area, it'd be great to connect with you at that. We've got a workshop and panel at Supercomputing, also course papers and presentations at HPC Asia. This is me. If you want to reach out, this is my email address. As I say, I'm also going to be around from the Tuesday, so please just grab me. It'd be great to have a discussion, and please also join the HPC SIG. Thank you very much, and have a great rest of the day and a great rest of the summit as well. And I'll see you there hopefully.